Arithmetic sequences fit very nicely into functions. You have a pattern and you have a rule, and then we're going to look at different formulas that you can use to describe those functions, those patterns. So our target is that I can identify and extend patterns and sequences and represent arithmetic sequences using function notation. So a sequence is not anything that's new to you. It's an ordered list of numbers that often form a pattern, and each number in that list is called a term. It's a term of the sequence. It's different than a term in an algebraic expression where it's the words that build the phrase, like 2n or -5x. It's not that kind of term. It's each number in that sequence. Now, sequences can be put into two different categories. You have arithmetic sequences and you have geometric sequences. You've worked with both of these in the past. An arithmetic sequence is where you have the difference between consecutive terms is constant, and so since it's difference, you're talking about subtracting or adding a negative, and that difference is called the common difference. With a geometric sequence, the ratio of any term to its preceding term is constant, and that's called the common ratio. So basically, to boil those down, arithmetic sequences, this is where you're adding or subtracting between terms. And a geometric sequence is when you are either multiplying or dividing by terms. So that common ratio is what it is that you're multiplying or dividing by. The common difference is what it is that you are adding or subtracting between your terms. Here is an example of an arithmetic sequence, which is going to be the focus of the lesson. We're not going to be looking at geometric sequences in this lesson. That will come later in the year. So from 5 to 8 to 11 to 14 to 17, each time you're adding 3. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14, and so forth. You've been looking at sequences like this since elementary school. So the pattern in this sequence is add 3. And then if you wanted to find the next couple of terms in there, you would add 3 to 17, which would be 20. And then you could add 3 to 20, and then the next term would be 23. Pretty easy there. In other sequences, it might be that you're subtracting each time. It might be that it's a decimal or a fraction that you're adding or subtracting. But whatever that change is between your terms, it's a constant change. You are either adding or subtracting. Now let's look at the different ways that you can express that sequence. You can do this with something called a recursive formula or the explicit formula. The recursive formula, think about that, recursive. If it's like you are reapplying for something, that means you've applied once and you're applying again, a second or a third or a fourth time. So this is a reoccurring pattern that's happening. It's a function rule that relates each term of a sequence to the one before it. So let n equal the term number in the sequence, like the first term, the second term, the third term. That's what n is going to represent. So a of n, this is function notation here. If you'll remember before we talked about f of x or g of x, when it has capital A of n, that means it is an arithmetic sequence. That is the value of the nth term in the sequence. And so if it said a of 2, that would be the second term in the sequence. If it said a of the 16th, that would be the 16th term in the sequence. So the value of term 1, a of 1, the first term, is 7. The value of the second term, I find that because of the 1 before it. I take the first term and I add 4 to that. 7 plus 4 is 11. The value of the third term is determined based on the 1 before it. So the third term is equal to the term before it, the second term, which was 11, plus 4, which is 15. The fourth term is determined by the 1 before it, so the term before the fourth term is the third term. I add 4 to that. 15 plus 4 equals 19. So we're adding 4 every time. That's why the common difference is 4. Here is the recursive formula. So the value of term n, if I'm wanting to know any term, if I'm wanting to know the 15th term, the value of, say, the 15th term is equal to the 1 before it. 15 minus 1 will be the 14th term plus 4. So what is kind of a holdback to the recursive formula is you have to know the term before it. It will be very difficult to find the 117th term, because you would have to know the 116th term. To know the 116th, you have to know the 115th term, and so forth. So what is useful about the recursive formula is if you know the term before it, it's very easy to find the next term. So whatever term it is you're looking for, you look at the term before it. That's what n minus 1 is. That's 1 before it, 1 minus that, or 1 subtracted from that. And then you have the common difference. Common difference is 4. That's where it goes. It's the value of the previous term. That's what in blue n minus 1 is, plus 4. So for this situation, the recursive formula for this sequence, a of n, is equal to a of the previous term, n minus 1, plus 4. So the only thing in that is that's actually specific to this pattern is the plus 4. The rest of it is generic. It's going to say a of n equals a of n minus 1 every time, and then you're going to have the common difference. But to do that, they also have to give you the starting point. They also have to tell you what the first term is. A of 1 equals 7. The explicit formula is where you can find the 116 term. It's a function rule that relates each term to its actual term number. You want to copy this diagram down, and this is something that we're going to refer to quite a bit. And I've pointed out each of the parts of this formula so we can keep everything straight. Now, where that says a of n, it has n down there, that is the same thing as saying capital A of little n. It's the same thing. It's just written different ways depending on where you look at it. Your textbook writes it like this. That equals a of 1, which is the first term, plus the previous term times the common difference. So this first part, the nth term, and that will always be there, you're not really going to change that, is equal to whatever that first term was, plus, this is the term's position, is n minus 1, the previous term, times whatever that common difference is. Whoops. So if you were to take this one that we were starting with before here, our first term was 7, our common difference was 4. So let's record that down here. Our first term was 7, the common difference was plus 4. So if I were to write that same sequence using the explicit formula, a of n would be equal to 7 plus whatever the previous term was times 4. That's what that would look like. So then if I wanted to use that, like I said, to find, let's do the 20th one. So if I'm wanting to find a of 20, the 20th term, that's going to be equal to the first term plus, I'm going to put 20 in there, 20 minus 1, times the common difference, which was 4. Let's drag this down, give us some more room. So the 20th term is equal to 7 plus 20 minus 1 is 19. 19 times 4, we'll do that next. A of 20 is equal to 7. Hopefully your pencil's working better than mine. Plus 19 times 4 would be, let me think, 20 times 4 is 80, so minus 4 would be 76. So the 20th term, come on, there we go, would be 83. So that is a good use of the explicit formula, is you can use it to find any term in the sequence. I could use that same formula to find the 116th term. You would just plug in 116 where you see 20 and just go ahead and calculate that out. So if you wanted to write an explicit formula, here's a pattern being shown here. The first term is 3. The second term is 7. The third term is 11. The fourth term is 15. And your common difference is 4 there. So my formula, I'm going to keep a to the n, or like I said, you could write that as a parenthesis n. It means the same thing, equals the first term, which was 3, plus n minus 1 times the common difference, which was 4. So right there would be our explicit formula. Okay, now let's see about converting between the two. You start with the recursive formula and you want to change it to explicit. So here is our kind of cheat sheet of, you have that on your notes, of what the explicit formula looks like. In the recursive formula, the key parts here, that 2, that is your common difference, that is D. And 21 is your first term, A of 1. So to write it as an explicit formula, that's going to be A of n is equal to the first term, 21, plus n minus 1 times the common difference, which is 2. So that's that same pattern, that same arithmetic sequence, but this time it's written in the explicit formula. On the other side, we're going to take an explicit formula, A of n equals 76 plus n minus 1 times 10, and we're going to change that to the recursive formula. So with the recursive formula, let's look at this one over here. You still have A of n, and that equals A of n minus 1, and what that is saying is the value of the previous term plus the common difference, which is 10. And then you're also going to add in what the first term is. So I would put semicolon, I'll bring it down here because I'm short on room. A of my first term is 76. I can see that from down here. A of 1 is my first term, and that is 76. So there it is as the recursive formula.